Everyone. Um, on module 13, we're going to focus on analog to digital conversion. So this is a second half of interfacing analog system and digital systems together. That way, because the real world is analog, right? So if you make some sound like what I'm doing right now, right, I'm speaking into a microphone, but the sound waves that I'm creating are actually analog, where it's an oscillation of multiple frequencies added together. Or if you even take a picture, right, which we see in RGB, meaning red, green, and blue, right, the amplitude of the amount of light you see in your photograph for each color, right, that's actually an analog. Um, if you want to talk about technically, if you're counting down to single photons, or if you do have a discrete system, so that you can digitize that without having analog digital converter, but we're not gonna. Let's just talk about in general, like big, regular photographing. Is actually analog. Okay. If you're measuring temperature, right, of maybe your car battery or something like that, so it doesn't shut down or explode, right, that's important. That's an analog value. The pressure in the atmosphere, right, or if you go into the moon, and then you need, pressurized suits, right, to make sure you're alive, that's important. In fact, all the physics values that you use to learning, right? Position, velocity, acceleration, those are all analog values, right? So somehow we have to convert that into binary or digital data, and that way the computer can record it. And then previously we taught you how to convert it out of the computer. Now we're going to try to do this conversion into the computer, right? So the little example here, I just found this guy talking into a microphone that probably looks like me right now. Um, and oops, actually the camera is off, so that's why you can't see me. There he goes. Sorry about that. Okay, so I was talking to the microphone, and then when I was growing up as a kid, we actually have to buy these things called a sound card. It's basically an analog to digital converter slash digital to analog converter that allows you to convert the digital data into sound or record sound from a microphone. But now these are all built into a motherboard on the computer, so we don't actually have a separate card for that. But this is one of the application, converting sound waves into binary data. So going back to our cosine waves, let me see if we can go up here. Okay, going back to our little cosine wave example, I have a cosine wave that has a frequency of 10 hertz, an amplitude, well, has an amplitude of 1/2 plus 0.5 minus 0.5, but it's centered around 0.5, so it actually goes from 0 to 1. Um, and remember the idea of analog to digital conversion. Okay. So this cosine wave example, so what we want to do is sample multiple points on here, and that way we can figure out where the peaks and the valleys are, right? So it's, not all waves will have this nice pattern, right? You're gonna have some wiggly waves, but this is just a simple way to figure out, oh, well, let's start with this point here, right? So this is 0.5, 0.6, 0.7, maybe 0.75 up here, right? How do I convert that information into digital, right? Because this is a wave since it's analog. So I need to convert that to, like, some sort of ones and zeros, right? Somehow. Okay. This is where on all the analog to digital converter, also known as ADC, so I'll start using that acronym a lot, uses comparators. So I want to give you well, this was covered in lecture 60, so if you want a full reminder of it, please go back and watch that lecture. But a comparator basically is an op amp where you remove the feedback loop, so you don't get a feedback. Where the output of this op amp, right, it's going to be this open loop gain, this A. Uh, um, don't worry about what that number is, but but this is proportional to basically V plus minus V minus, right? So these are the two inputs on this side. So whenever V in plus is bigger than V in minus, you're going to get a huge amplification. And usually what happens is that that amplification sends your output up to whatever your VCC voltage is. Okay. Okay, this is known as railing, right? It just goes up against the VCC voltage. But if V in plus is less than V in minus, right? That means this number here is going to be negative, right? This gets amplified by 10,000, 10 million, whatever it is, right? But it's going to get railed against the negative voltage, because if this difference is still slightly negative, it's going to go to negative voltage, which is going to be your VEE, or sometimes on a lot of digital system, that's actually going to be ground. Okay, so if this is positive, then you rail against the positive voltage. If it's slightly negative, it's going to rail to the either ground or your VEE, whatever your lowest voltage is. So the book has a example of a flash ADC, which is what you would think would make sense to begin with. It's actually the simplest type of ADC, but usually we don't use it. Okay. The book actually made a little mistake. This is actually supposed to be 3 volts. Let's do that. Let's cross that out. Okay. So this is a 2-bit ADC, so it can store up. You can have the digital output can either be 0, 1, 2, or 3, or in binary 0, 0, 0, 1, 1, 0, and 1, 1. Okay. On the left here, you have your analog input. This is analog, right? Yeah. So this will be your, your little wave function, whatever you're sending in. Okay. And then right when these gets inputted into these 3 comparators, so these are all your comparators. If I can write, please, one note, stop doing that. Comparators, right? Comp. Remember, these comparator just compares the 2 inputs. If it's positive, then it goes to high. If it's negative, it goes to, well, in this case, it's going to go to 0 instead. Okay. Okay. But the other inputs are through this long resistor chain here, where you have R here, 2R, 2R, and R. If this top voltage up here is 3 volts, not 4 volts, okay, I'll let you do the little calculation. What happened is that these voltage divider actually sets up this voltage here, where is the inverting input, or V in negative here on the first comparator, C0. Okay, it's going to set it up at 5 volts here. It's going to set this voltage up at 1.5, this voltage up at 2.5. And then these are going to be the threshold voltage that we're going to think about when we're analyzing this Vn. Okay. So what happened is that when Vn, right, let's do some checking, right? So let's say Vn is 0. Let me write. Okay. If Vn equal to 0, let's write that. Right, it's equal to 0. What happened is that you get ground, ground, ground to all the positive inputs. Okay. Since, right, these comparator compares the 2 input, right? If it's ground here, well, ground is not bigger than 0.5, so therefore, right, this comparator actually, the output will go as low as possible. In this case, the output here will go to 0 volt, right? If we're supplying this to ground, and then the positive voltage is VCC, which will be probably 3 volts up there. Okay. All right. Well, okay. So that's not that interesting. So that's going to happen until, right, you cross this 0.5 volt thresholds, right? So I'm going to stay away from that threshold. I'm going to talk about what happens if you're around that threshold. Let's say I get to 0.6 volts. Now, right, if it's 0.6 volts, zoom in a little bit, right? Now, right, 0.6 volt, 0.6, 0.6 up here. Right, now this comparator, right, is going to rail to VCC instead. So this goes to high, whatever that is, right? In this case, 3 volts. And it's going to output this to be a high state, whatever the logic that is, okay? The rest is going to be still 0 because it's still less than 1.5 and 2.5, okay? All right, let's do one more example, and then I think you guys are already starting to see what this pattern is. Let's say I go up to 1.6 volts, right? Right now, this comparator is high, right? And then if I increase the voltage here from 0 to 1, 1, 1, why I put black? So red, 1, 1, 1, right? Now this comparator also goes high. So C1, so C0 equals to 1, everything else is 0. C1 goes to 1, and then C0 also is 1. Okay, both of those go high, but C2 is still 0. Okay, once you reach 2.6 volts, right, that's when all 3 comparator goes high, right? So C0 equals to 1. Okay. Okay. This gets inputted. So now these outputs here are actually digitized, but right, we need to arrange them into the right bits, and that way we can actually see which one are have the correct binary structure. Okay. So to do the logic here, it's written out here, but I'll just kind of draw the logic that you see. So basically what happened is that, so you have these 3 comparators, right? I'll do a pretty simple version of this, right? Plus minus. I'm not going to draw the resistor chain because that's just going to turn into a big mess, right? So the output here, what you do is you put these through a series of XOR gates. So this is an XOR gate, right? And this is exclusive OR. So that means the output is only high when one of the input is high, not both, okay? And we're going to see where that goes. This doesn't go to the output directly yet, okay? And then you basically split this, okay? Oh, and there's one more on top where you have this, and then the top one is tied to ground, okay? You have 3 lines coming out here, 3 comparators, 3 XOR gates. Okay, so what these output goes to, I'm not going to throw in the diodes yet, but what these output goes to is this is going to be directly tied to basically Q0. So this is C0, sorry, up here, C0, C1, C2. Okay, this is going to go to Q0, and this is going to go to Q1, but there's a special way you have to route this, because what happened is that if the output is actually the C3, which is the 3rd comparator, output is high, you actually want both of them to be 1. Okay, so we're going to see how we can do that. Okay, I'll add the diodes in later. Sorry. Oh, there's something additional to do with it, but right, this goes to Q0, Q1, and this goes to Q0. And what happened is that you actually want to route the 3rd output also to Q1, but then also to Q0. Because when you have the 3rd comparator high, right, C2, you want both of these to be 1, right? So you want both of them to be high. And we're going to have a little truth table, conversion table check back here. One more thing I'm going to add. Whoa, these are erasers. I'm going to add diodes. So these are not gates. These are just regular diodes to all of these. This prevents the current from flowing backward through the back to the output of these XOR gates. Okay. All right. So let's just check, right? So if the voltage input is, less than 0.5 volts or 0, right? That's what we expect. If it's 0 here, right, then all these gates are low. Then both of these Q and Q0 and Q1 are both low. Okay. If it's between 0.5 to 1.5, that's the threshold for the first comparators to go high, right? This is this area here, this voltage here. Then only the lowest comparator goes high. So that means this comparator, I can stick with green, right, goes high. Okay. When only that comparator goes high, right, this will go here and makes Q0, right, 1, but then Q1 stays at 0, right? So that's what this is. Okay. But with the voltage between 1.5 to 2.5, right, that means it passes the second comparator. Okay. Since this is an exclusive OR, if both of these are high, right, both C1 and C0 are high, since it's exclusive OR, this actually go low, right? Right, so you get 0 at Q0, okay? But since this is, but this signal is high, right? C2 is still 0 because you haven't crossed the C2 threshold yet. This is just 1 and then 0, so the exclusive OR of 1, 0 gives you a high, and then you pass through this diode, and then you get Q1, 1. Okay. Once you cross the highest threshold, which is above 2.5 volts on top, okay, that means it's all the way up here, right? All of these comparator goes high. You get 1, 1, 1 at the comparator input outputs, okay? But you have to go through this exclusive OR gate first. Exclusive OR of this, right? Since it's 1, 1 is going to be 0, so Q goes low. This output here is low. It's not Q yet, right? And then both of these inputs are high, right? That means this output here also goes low. But you have this last link up here to the exclusive OR gate, and the top of this exclusive OR gate of this ladder is always going to be tied to ground. So whenever this is high, that means this is going to go high. So you're going to have 1, 1 going through Q1 and Q0. Okay, and therefore you complete the 2-bit analog to digital conversion. So this is really neat, right? Conceptually, the logic is very simple. And the cool thing is that it's very fast, right? As soon as the signal on the left-hand side changes, right? Any changes on the left-hand side, right, is basically propagated at the speed of light, right, to the right-hand side, right? So depending on how long the wire is, if the wire is only a few centimeters long, right, and then you have to go through this gate, which has a little bit of propagation, on the order of maybe fractions of a nanosecond. So you'll have your output in nanoseconds, okay? And then this is called flash ADC because it's fast, okay? But it also costs the most. Okay, why does it cost the most, right? So that doesn't seem like a very expensive circuit, right? To do an n-bit conversion, basically you need 2 to the n minus 1 comparators. So you can see how this is going to start scaling up very, very quickly. And then the number XOR gate is the same. So because for every comparator you have, you need an XOR gate. Okay. Because these are not number of bits, right? This is the number of levels you have. Okay. I'm not even considering the resistors, so actually you probably have to diodes and resistors, right? You have a bunch of resistors in there. So that's going to be approximately also about 2 to the n. Actually, it's actually more than that. The number of diodes you need, because in order to protect these channels, you're gonna start seeing channel that has like 3 inputs coming down. So you actually have more diodes than there are number of levels that you're trying to do. Okay, so let's say we want to do a 14-bit flash ADC conversion that gives you 16,000 levels of analog to digital input. Okay, so that's 16,000 comparators, XOR gates, and probably that number of comparator times 10 of that number, probably like 160,000 diodes and resistors you have to deal with. A lot of stuff. Okay, so I didn't even account for the cost of the resistor, so let's add that in. So let's say the resistors are also like 5 cents or something like that, right? Not that much. even less than that probably if you buy in bulk, right? Comparator is like 50 cents maybe. The XOR gate is 10 cents. And then the passives, the diode, meaning the diodes and the resistors, are another 10 cents. So each level, right, costs about 70 cents each. Well, that doesn't seem a lot. But to do a 14-bit conversion, you need 16,000 channels. So you take 16,000 channels, not 16,000, 16,000 levels, right? So that costs more than $10,000 to do a 14-bit analog to digital conversion. Okay, so that's a lot more than your phone, your computer, stuff like that, right? So generally, these are not used in consumer electronics where you know you want to do an analog digital conversion, but the speed is not that important. Okay. Um, but it is the fastest because the conversion, I mean, it's even less than one clock cycle. It just happens right away. So these are typically applied for where speed of converting analog data to digital data is extremely important, such as radar guidance systems. So if you're shooting something into space, for example, or up to the air, and you want to track something and you want to be able to guide that missiles to your target, right? You're using a camera that has some pixels on it, and that's actually able to detect which direction the target is in, right? You want to convert that information from analog to digital as fast as possible. Do a little FPGA to do a guidance program in it, okay? And then send that feedback to your fin so you can actually direct things in the correct way so that you actually are homing in on the target, okay? So these are usually how a lot of these rocket system works, where you have a two loops, where you have the infrared loop and then the guidance loop, where basically this is where all your optics are, okay? And then the electronics part, which is the, let's see, IMU, so where the synchronization and IOs are, this is where a lot of your electronics are, and it's an essential part of this loop in order for you to get the information as quickly as possible. That way you can actually use it in order to figure out how to change your trajectory, let's say, if you're doing that. Okay. Of course, this is not the only application. So a lot of physics experiment uses this. For example, the experiment on the neutrino detector, we sample every 2 nanoseconds, right? And anything other than flash ADC will be actually too slow to do that because it does, unfortunately, the speed of light is finite. So for the information to travel through, a couple of feet of signal of wires, right? That's already take 2 nanoseconds. So that's usually like the almost the very best speed. There are better analog to digital converter that can have on these experiments, not these missile guidance systems, um, on these experimental stuff. Because for experiment, we don't care. We're not just looking at like 10 or 15 channels, right? We have a detector. We may be looking at millions of channels. So you take that $10,000 and you multiply that by a million, you're gonna run out of money very fast, let's say. Okay. And sorry, I was talking about analog digital converters for physics experiments. There are those that are faster than what we use, which has a half a nanoseconds timing, a sampling rate, sampling for period. The ones we're using right now are 2 nanoseconds, which is about 4 times um, slower than the best, but it was cheaper, so that's why we use it. But they still cost about $10,000 per channel. Okay. So since obviously, my microphone here, right, and my cell phone, all of these cost less than $10,000. So how do we do analog to digital conversion without paying that price? And this is where you're doing successive approximation, register. I don't know why the book doesn't write that. Register. So there's actually that part also. ADC. Okay, this is typically what you see in consumer electronics. So the way this works, it works off just one comparator. There's a few other electronics bit, and then you're going to have a register here, and then you have a digital to analog converter, which we learned about last time. Okay, so the way this works is based on a binary search algorithm. So what I'm going to do is try to zoom out here so we can take you through the logic of how this works. Okay, because I want that bottom picture in there too. Okay. Okay, let's say we're doing a 4-bit analog to digital conversion. Okay, and the input is 9. Okay, so the input here is 9. Let's set this voltage at 16. Usually you don't want to go that high, but I just want simple numbers. I don't want to deal with fractions. Okay. All right. So how does this 9 gets into converted into a bunch of ones and zeros? So 9 is actually 1001, which is what's going to be recorded on these registers on the other side here. Okay. So let's see what happens. So you have this 9-volt input, right? You go through this comparator that's comparing to something. Okay. The first time out, what's going to happen is just going to compare to 0. It's actually kind of a boring step. Okay. So, well, obviously 9 is bigger than 0. So this comparator gives you true as the output. Okay. And that output gets sent over here. So this is just a pull-up resistor. So to keep the voltage at high at, oh, I don't want that. Yeah, that's going to be too high. Okay. Yeah, let's keep that at 5 volts. Okay, so that is correct. Okay, so it's going to pull up here. So it's going to pull it up so you have 5-volt TTL logic, most likely. Okay. And this is going to be some logic in there. Okay, that's going to register. Okay. If you're telling it true, what is going to happen is it's going to start it's not a counter, it's like an opposite counter. You're going to flip this bit up to 1. So the first time out is going to flip this bit up to 1. Okay. What happened is that while that 1 is going to get stored in this register, so I'm going to erase this because that's the answer. I'm cheating there. Right? The first time out, right? The first loop through this is going to store that. Okay, and it's going to also send that information back out to here. Okay, right. All of this takes a little bit of time. In order to synchronize all of this, we're going to synchronize this to a clock. Okay, there's a clock here that's going in, and these clocks has to be synchronized with each other. In fact, there's a clock going in here also. That's going to tell you when you're ready to be read out, stuff like that, which is stuff we learned last time too. Okay, so now this is output, but this is a digital to analog converter. So 100 here, right, is actually equals to 8. So I'm gonna, the second round goes through, this voltage here is going to turn to 8. Input is still 9 volt. This doesn't change, right, because that's actually your input. Okay, 9 is still bigger than 8. It's going to flip up once again. Okay, so this comparator is high once again, but when the second time it goes through, it sees that, oh, well, you already have 1000. What I'm going to do is I'm going to flip one more bit, which is going to be the next one, okay, to be 1100. Okay, and that gets forwarded to the register. Okay, and then it gets forwarded to your DAC. And now this value, instead of being 8, right, the next time it goes around, this is going to be, well, right, 1, 1. So that's 8 plus 2, no, 8 plus 4, that's going to be 12 volts. Okay, well, now it's different now, right? Now 9 volt is actually less than 12. Through this comparator, this is actually going to go low or go to 0. Okay, when this register when this SAR, right, this approximator is receive a low signal on the next clock pulse, what's going to happen is that instead of modifying the next bit to be 1, it's going to shift this bit over instead. Okay, what's going to happen is 1010. Okay, right? And then that's going to get stored in your register, and it's going to get copied over to your DAC, right? Now this value, right, is not 12 anymore, right? This is 8 plus 0 plus 2. So now this is actually at 10 volts. So this DAC will output 10 volts. Now, right, 9 volt is still bigger than 10 volts. So the next time it goes around, it still goes low, okay? When it goes low again, right, it'll, instead of uh, shifting one of the bits to be 1 or 0, sorry, changing one of the bits from 1 to 0, it's going to do a shift once again, okay? And this is going to give you 1001 as the recorded in the register. And then we're going to go back here. We're going to get 100. And then that's going to be exactly 9 volts, right? That's the answer. Okay. Long process, right? And this is just to do 4 bits. Okay. So if you're doing 14 bits, this is going to take so many more cycles, right? Okay. So hopefully now you can see that, wait, yeah, this is a much more laborious way to do it, but you only need one comparator, right? One of, well, these registers that you want anyway, right? Because you're storing this information because you're going from analog to digital. And then you need to build a DAC, which we know how to build from last lecture, okay? All right. So this works on the same principle as a binary search. So those of you who are, you know, gone through like a computer science class will probably have done a binary search, right? The idea is that, right, you make a guess, and the first guess is you guess the middle number. So if I tell you, you know, which number am I thinking about between 0 and 15, your first guess should be 8. Okay, that's the middle number. And then I'll tell you, is the number bigger or less than 8? And I said, yeah, I said it's bigger. Then you guess 12, right? Because that's a binary search. Okay, this gets you to, so 8, and you get 12, right? And then you can ask me, oh, is the number bigger than or less than 12? Then I said it's smaller. Then you go to 10. That's your next search. Okay. And then the next thing you ask me, oh, is it bigger or less than 10? And I said it's smaller. Then you go low once again. You're shifting these bits over, and then you end up at 1001, which is the answer. Okay. So the number of guesses you need to do, right, is equal to the number of bits of your output, right? If you're doing 4 bits, then you have to do at least 4 guesses. If you're doing 8 bits, you're going to do 8. If you're going to do 14 bits, you're going to guess 14 times. But, right, be a little careful, right? These information gets transferred over multiple things, right? Each guess takes a few steps, right? First of all, the comparator has to do it, right? That information gets sent into these logic gates, which has, you know, 1 or 2 cycles in it. So each guess already take, like, let's just count that as 1, okay? And then it has to register that number into your registry, and then it has to send that data over to your DAC, the digital analog converter, right? And that has to get recorded there. And then the next step is that it has to send that information back to the input comparator, right? So every guess takes about 5 cycles. Did I do this right? And oh yeah, I was going to go into detail a little bit more on this in next lecture instead. Okay, but okay. So one thing that there's a little bit more detail about how ADC works, which is what the textbook covers. So I was going to go over that. There's also these double versus dual slope ADC. This is really neat because when you're sampling your signal, right? This signal here, right, is not staying constant. And we're going to talk about these things called sample and hold. That's going to allow you to hold this for, you know, a microsecond so you can actually read it out. But the important thing is that when you're sampling, this doesn't happen instantaneously. Okay? The simplest way to sample a voltage is by doing the single slope ADC, which is just basically whatever your signal is, your analog input is, right? You have a little switch, and then you just connect this to this top of this capacitor, okay? And by measuring the voltage across this capacitor, you're able to figure out what the input voltage is, okay? So you have the switch that you can flip up and down, okay? When you flip that switch, what's going to happen is that it's going to charge up this capacitor, right? As this capacitor charges up, right, it's going to take a little bit of time. So if we model this charging of a capacitor as a linear function, which technically is not, because as you go towards the highest voltage, what happens is that it'll just get leveled out, okay? But you're actually sampling, you're actually measuring this, you know, way before that, and that way you actually have a pretty straight line, okay? So you can model that as, you know, well, if the voltage across that capacitor is going to be proportional to the amount of current going through it divided by the capacitance of your capacitor times T, the amount of time you're actually doing your sample, your charging up, okay? That allows us to figure out what VC is, okay? But this relies us on knowing exactly what the capacitance value is, okay? So if your capacitor is off by 10%, then your measurement is going to be off by 10%. Let's say you design your circuit, thinking that it's going to run at 10 Celsius in a pretty cool room, right? But then someone brings it into the sun, and now it's like 30 Celsius or even 40 Celsius in Turlock, right? Then it's going to run hotter, and then so that capacitor, right, is supposed to be spacing very tightly together, expands a little bit, right? That's going to cause a difference in this capacitance, and so even temperature variation is going to cause a problem if we're just doing single slope ADC. So the idea is that we're going to do a dual slope ADC, just to describe this little method a little bit. Okay, a dual slope is that you do the measurement twice. Okay, so it's kind of a, I think the book, would have been nice if they put that in. So you have this, model where you're charging up the capacitor to whatever VC as a function of time is, right? And then you discharge it, okay? Okay. And this discharge, right, is modeled so that it's similar to what the charge rate is, okay? So the first side is still the same, but what we're going to do, oops, I should not have done that, right? The first charging, you're still doing the same thing as what we did before, where VC as a function of time is still the current divided by the capacitance times this time, right? Whatever that is, and that'll allow you to calculate the voltage at the input, right? In fact, what you do is you measure up into this time called tau. Okay, we're going to do this. We're going to change this out. Well, the book does it, so I'm going to do it just so you can understand what the book is doing. We're going to change this current into alpha Vn, right? Because the amount of current that capacitor is going to receive, or it's going to be proportional to how much, how high the voltage is that you actually have at your analog input. So this is actually your analog input, right? Okay, so replace that. So we're just replacing the I with that. Okay, hopefully that's not too bad. And we're measuring up to tau, where this is the tau point. Okay, then what we do is we disconnect it from the capacitor, disconnect V in from the capacitor, and now the capacitor is going to slowly discharge. Okay, okay, all right, we're going to discharge the capacitor. When we discharge the capacitor, the current is not going to be the same, of course. We're going to call that I prime. Okay, and the amount of time we measure for is delta t. So this is tau. You measure up to tau, and then you measure, after you disconnect it, you measure another time longer, delta t. So that's why the total time is going to be tau plus delta t. Okay, that you're doing this measurement for. Okay, well, if you solve this equation for delta t, it just turns into c over I prime with c VC on top. Okay, right? But the cool thing is that VC, you already know what that is, right? VC at tau, which is the maximum charge you have up here. So we can replace that with what we have up here, right? And therefore, the C's actually cancel each other out. Now, in this case, right, this method of sampling what the voltage is for the ADC no longer depends on the capacitance. Okay, and that's the cool thing about it. And then now you have just this alpha times tau, if you solve this equation, divided by I prime, and that's going to be proportional to your Vn. So if you're interested in your Vn, you just have to solve for delta T times I prime, which you can measure, divided by alpha times tau. Okay, and that's what your Vn is. All right. That's it for this lecture. So next one, I'm going to show you how we actually uh, run a successive approximation ADC on a breadboard. And then the third lecture is going to be on how do we do that on FPGA instead. Okay, thanks.